Modern urban living has a hidden indoor air quality crisis that few outside the building science profession ever notice. Because the recirculating HVAC systems most people rely on at home and work actually fail to remove a striking share of the dangerous indoor pollutants that accumulate invisibly every single hour of every day. Victorian builders, working more than a century ago without any of our modern fan technology, solved this exact problem with quiet passive pressure differentials that naturally pull fresh outdoor breezes up through the floorboards of every occupied room in the building. Those forgotten gravity-driven ventilation shafts operate today in tens of thousands of still-occupied older buildings and outperform our loudest modern mechanical fans in measured fresh air delivery per kilowatt of energy used to power them. Here are the 5 evidence-backed atmospheric forces that have quietly made modern airtight buildings much sicker inside than the supposed crude Victorian rooms next door, and the practical architectural moves that can bring real fresh air back into today's living and working spaces. The first chapter lays out the full scope of the modern crisis of stagnant indoor air, which is one of the most poorly appreciated public health issues of the contemporary built environment today. The United States Environmental Protection Agency itself has officially estimated, and this specific figure is widely cited across the peer-reviewed building science literature in the United States and Europe, that indoor air can commonly be 2 to 5 times more polluted than outdoor air at the very same moment in time. And in some specific indoor environments, the measured difference can be as much as 100 times worse than the outdoor baseline at the front door of the building. According to the same federal agency estimate across multiple studies, it has referenced in its published reports. Since, according to standard population surveys from the United States and Europe, most adults in fully industrialized countries spend roughly 90% of their total daily time indoors across the entire year. The cumulative chronic health exposure implications of that measured difference are genuinely profound and largely unappreciated in public health messaging. Yet indoor air quality remains a relatively low-priority concern in mainstream public health discourse, precisely because the entire pollution exposure is invisible to the eye, and its health effects accumulate gradually over years, rather than manifesting as any recognizable acute illness that an individual would even notice forming. The indoor pollutants responsible for this measured daily degradation of indoor air come from multiple overlapping sources in any modern occupied building at any time of day. Volatile organic compounds, often shortened to VOCs, off-gas continuously from synthetic modern building materials, fresh paints, strong adhesives, mass-produced furniture, and the chemical ingredients of ordinary household cleaning products at a steady measurable rate. These include measurable formaldehyde, continuously off-gassing from composite wood products like particle board shelving and cabinets, measurable benzene from certain paints and adhesives, and measurable toluene from numerous ordinary household materials in regular use. Fine particulate matter, written PM2.5 in the air quality literature, refers to particles small enough to penetrate deep into the lung tissue, and in some measured cases, cross physically into the bloodstream through alveolar gas exchange. Indoor PM2.5 is actively generated by cooking, scented candles, indoor tobacco smoke, office printers, and many small appliances, and it steadily accumulates in tightly sealed modern indoor environments across every single hour of the day and night. Carbon dioxide itself builds up continuously wherever people simply breathe normally in unventilated or poorly ventilated interior spaces, with measured CO2 concentrations above approximately 1,000 parts per million, while typical outdoor air sits around 420 parts per million, directly associated in published research with measurable declines in cognitive performance, particularly in tasks requiring active decision-making and information processing. Biological contaminants including active mold spores, dust mite allergens, accumulated pet dander, and airborne viruses and bacteria also steadily accumulate in recirculating indoor air systems across every working day in tight modern buildings. The second chapter explains the elegant Victorian stack effect that powered fresh air delivery in older buildings, with no electricity required at any point in the operating system. Victorian building design, particularly in Victorian Britain from roughly 1837 to 1901, and extending into the parallel Edwardian period, and paralleled in contemporary American and European construction across the same decades, incorporated passive ventilation as a deliberate and engineered architectural feature. This Victorian design philosophy was driven by a combination of practical building necessity and an actively developing scientific understanding of indoor air quality and basic public health in dense urban centers. The mid-19th century urban public health movement, vigorously galvanized by the miasma theory of disease, which was ultimately incorrect about the specific biological mechanism of disease transmission, but was entirely correct that foul-smelling, stagnant air correlated strongly with illness and death, drove systematic and evidence-based attention to architectural ventilation in both domestic and institutional building design across every major British city. The physical principle underwriting all Victorian passive ventilation design is the stack effect, also called the chimney effect, which quietly exploits the basic thermodynamic properties of air at different temperatures throughout the working day. Warm air is measurably less dense than cool air at the same pressure, and therefore less dense air naturally rises in any enclosed vertical space over time. In a tall building with vertical open shafts or open interior spaces, whether purpose-built dedicated ventilation shafts, open stairwells, or original chimney flues, warm air generated by the human occupants and by solar heating of the building fabric quietly rises naturally through these vertical channels, mechanically creating a measurable low-pressure zone at the bottom of every open shaft. This continuous low pressure mechanically draws cooler outdoor air in at the lowest occupied level, through floor vents, through underfloor channels, or through low-level wall openings in the foundation walls, which then itself warms as it enters the occupied space, rises through the building, and exits through the open roof or upper-level vents, creating a self-sustaining airflow circuit that requires absolutely zero mechanical electrical energy to operate continuously. In Victorian domestic and institutional buildings of every scale, this elegant thermal principle was implemented with quite considerable architectural sophistication and real engineering care over decades of practice. Subfloor void spaces, the open cavity between the natural ground surface and the suspended timber floor that was standard across all Victorian construction, served as a continuous internal plenum for ambient fresh air delivery through the entire footprint of the building. External air vents in the masonry foundations, the characteristic cast iron or terracotta decorative air bricks still clearly visible in the external walls of Victorian houses up and down Britain today, allowed fresh outdoor air to enter the subfloor void, which was then actively connected to the interior of the occupied building through deliberate small gaps in the floorboards and purpose-built floor-level ventilation grills installed in the woodwork. Simultaneously, high-level ventilation, generously provided by transom windows above interior doors, by narrow ventilation slots above window frames, and by purpose-built ceiling and wall vents connecting externally to dedicated extraction shafts, allowed the rising warm, stale interior air to exit freely at the top of every occupied space. The third chapter lays out the detailed mechanical comparison between modern HVAC systems and Victorian natural physics, and the real-world performance results most people never see in any published comparison. Modern HVAC systems, formerly heating, ventilation, and air conditioning, represent a fundamentally different design philosophy from the older Victorian approach. Rather than working in concert with the natural physics of air movement, they impose air movement mechanically, against whatever ambient pressure differentials already exist in the building at any given hour of the day. This active approach offers significant practical advantages in terms of regulation precision, year-round consistency, and the ability to fully condition, meaning heat, cool, or dehumidify, the entire air supply before delivery into the occupied space. But it comes bundled with several significant and underappreciated operating disadvantages. Mechanical ventilation requires continuous electrical energy to operate at all, a recurring operating cost that represents a substantial fraction of any commercial building's total building energy consumption across a typical operating year. The cumulative friction losses throughout an extensive ductwork system, the wasted physical energy required to push conditioned air through the many sharp bends, multiple flow junctions, dirty filters, and heat exchange coils of any complex duct network, mean that HVAC systems are inherently far less thermodynamically efficient than the simple task of just moving air through space would otherwise suggest. A meaningful proportion of the actual fan motor energy goes into overcoming duct resistance and friction loss in the ducts themselves, rather than delivering properly conditioned fresh air to the human occupants of the building. And unlike passive Victorian architectural ventilation systems, modern mechanical HVAC systems require ongoing regular and costly maintenance, including frequent filter replacement, periodic evaporator coil cleaning, regular duct interior inspection, drive belt replacement, and refrigerant management that is, in real operating practice, frequently deferred or inadequately performed by building managers, with steadily degraded indoor air quality as the inevitable result across months of deferred maintenance. The active design priority of most mass-produced modern HVAC systems is thermal comfort, simply maintaining a desired set-point temperature inside the building, rather than indoor air quality or measured fresh air delivery for the occupants who breathe it all day. In many operating systems, the outdoor fresh air intake, the actual fresh air fraction of the designed air supply, is automatically reduced to minimum regulatory code levels during the active heating and cooling seasons, simply because outdoor air requires much more conditioning energy than recirculating already conditioned indoor air in any calculation. Building energy management systems, aggressively optimizing for short-term energy efficiency and operating cost, will frequently reduce outdoor air intake as a first-response energy-saving measure whenever the system sees any opportunity, even at measurable cost, to indoor air quality for the working occupants of the building space. The measurable CO2 problem inside modern buildings is particularly well documented in the published research literature and is directly measurable with inexpensive portable instruments. In a typical modern office building with standard published ventilation rates, indoor CO2 concentrations commonly reach 1,000 to 1,500 parts per million over the course of a regular working day, well above the 420 parts per million outdoor atmospheric baseline, and right into the measurable range where multiple published controlled studies have measured statistically significant impairments in decision-making quality, active information use, and measurable cognitive strategy in working adults inside the affected buildings. The fourth chapter lays out the actual published science behind how passive ventilation works in measurable detail through controlled airflow experiments and modern computational fluid dynamics modeling of identical building conditions. The physical science of passive stack ventilation is well established in modern building science and has been repeatedly validated across numerous published airflow experiments and explicit computational fluid dynamics modeling studies of standard building geometries over decades of research. The primary driving force, the measurable pressure differential physically created by stable air density differences between warmer interior air and cooler exterior air, scales linearly with the height of the active stack channel and with the temperature difference between inside and outside surfaces of the building. For a typical urban Victorian terraced house with an active stack height of 3 to 4 full meters of vertical channel, and an interior to exterior temperature differential of 10 degrees Celsius, which is genuinely common in temperate British and Northern European climates for the majority of the calendar year. The theoretical driving pressure differential is on the order of a few measurably small pascals. That seems like a small pressure, but it is more than fully sufficient to physically drive the airflow rates genuinely needed for adequate continuous ventilation of any residential occupied space across the entire working day. One of the most significant practical advantages of passive stack ventilation, in terms of measurable infection control and overall indoor air quality gain, is the clean directionality of its actual airflow field. Unlike recirculating modern HVAC systems, which create complex, turbulent, fully multi-directional air currents that can actively distribute airborne contaminants throughout an entire building and across multiple floors, a well-designed passive stack ventilation system creates a predominantly unidirectional straight airflow field. Cool, fresh air enters at the lowest level, moves cleanly upward through the occupied space, and exits naturally at the highest available vented point to the open atmosphere. Any airborne contaminants generated within the occupied space are carried firmly upward and out to the open air, rather than being recirculated back into the occupied breathing zone in the room. Recent published research on airborne disease transmission in indoor building environments, research that gained enormous additional prominence and major funding following the COVID-19 pandemic across every developed country, has consistently found that unidirectional upward airflow is one of the most operationally effective configurations for directly reducing the measured concentration of airborne pathogens and measurably reducing airborne disease transmission risk in real indoor spaces. The published residence time of airborne indoor pollutants, meaning the average measurable time a generated particle or airborne pathogen remains suspended in the indoor air before being physically removed through active ventilation, is a critical operational metric in indoor air quality field science. In a well-ventilated occupied space with scientifically adequate air changes per hour, written ACH in the standards, this measurable residence time is short. In a poorly ventilated sealed space, it extends dramatically across the working day in a measurable linear fashion. Carefully published research on passive ventilation systems has found that well-designed stack effect systems can consistently achieve 3 to 6 full air changes per hour under typical British and Northern European operating conditions without any mechanical electrical assistance, whatever. That published air change rate meets or actually exceeds the minimum ventilation standards officially recommended by ASHRAE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, for residential occupancies, and for many standard commercial occupancies across the United States and the broader English-speaking world. The fifth and final chapter explains in practical detail how passive ventilation principles can responsibly be brought back into modern buildings with available 21st century materials and existing engineering knowledge, and the quiet revival of passive ventilation principles in contemporary green building design is one of the most promising and measurable developments in modern sustainable architecture and formal building science in the last 20 years. Modern architectural implementations translate the proven Victorian stack effect principle into a full range of contemporary architectural strategies deliberately adapted for contemporary construction standards and modern aesthetic expectations of clients. The solar chimney is one of the most studied, most published, and most actually deployed of these contemporary approaches. A purpose-built vertical open shaft, glazed with glass or otherwise deliberately solar-absorbing on its full southern face, that amplifies the natural stack effect by actively using direct solar radiation to heat the air inside the shaft, measurably increasing the temperature differential and substantially driving greater usable airflow rates from entirely passive thermal sources. Solar chimneys can generate substantially higher continuous airflow rates than equivalent unheated open stacks of the same vertical height, making them genuinely and measurably effective even in warmer climates, with lower ambient temperature differentials between inside and outside air. Wind-driven passive ventilation strategies, including traditional wind catchers, deliberate courtyard designs, and the careful orientation of entire buildings relative to prevailing seasonal winds, safely extend the passive ventilation design toolkit well beyond purely thermal driving forces into measurable wind-driven airflow ranges, and traditional wind catchers in particular, which physically capture and direct prevailing breezes into occupied building interiors through directional openings at the elevated roof level, have been quietly used in Persian architecture for thousands of years, and are being actively studied, formally modernized, and sometimes retrofitted by contemporary building scientists for application in modern building practice today. Several genuinely high-profile contemporary landmark buildings, including the Eastgate Center in central Harare, Zimbabwe, which was explicitly designed by its architect to mimic the passive ventilation and thermal mass principles naturally found in African termite mounds, have publicly demonstrated that fully passive or near-passive building climate control is genuinely achievable at real commercial occupied scale in the 21st century building market. And the careful integration of passive ventilation design with smart sensor technology and selective mechanical assist thereby represents what many contemporary building scientists consider the optimal near-term working approach, with passive architectural systems honestly handling the baseline continuous ventilation load and minimal mechanical supplementary assistance, activated only when the passive thermal driving forces prove genuinely insufficient for the local climate conditions. Smart modern CO2 sensors, which are now genuinely inexpensive and very reliable in commercial use, can continuously monitor indoor air quality in real time and intelligently trigger supplementary mechanical ventilation only when measured concentrations meaningfully exceed preset thresholds for human occupancy, allowing modern buildings to minimize active mechanical energy use, while still maintaining consistent safe air quality outcomes for working occupants across every operating day. This deliberate hybrid passive plus smart sensor approach dramatically reduces net building energy consumption relative to conventional fully mechanical HVAC operation, while simultaneously achieving measurably better air quality outcomes than either pure mechanical or pure passive systems achieves alone in most published field studies to date. The broader published sustainability argument for passive ventilation, in the context of the entire global building sector's enormous cumulative energy footprint, is genuinely compelling in plain published numbers. Buildings today account for approximately 40% of total global energy consumption across most industrialized countries, according to standard IEA published estimates. And HVAC systems account for a substantial fraction of that enormous building total, with published estimates typically ranging anywhere from 30 to 50% of any single building's total annual energy use being devoted to active climate control alone. Any architectural approach that can deliver demonstrably comparable or actually superior ventilation performance with dramatically lower energy input represents a potentially major practical contribution to genuinely decarbonizing the entire built environment for the coming generation of building stock across the world. Low-energy ventilation solutions, including full passive, carefully designed hybrid passive-active, and demand-controlled mechanical ventilation approaches, are now centrally featured in every major green building rating system, including LEED in North America, BREEAM in Britain and Europe, and the rigorous Passive House standard from Germany, all actively driving their practical adoption into the mainstream commercial and residential construction industry through published certification requirements and buyer demand. Perhaps the single most enduring lesson from the entire Victorian ventilation architectural legacy is one of plain architectural humility. The very best buildings, measurably evaluated in terms of both genuine health outcomes for occupants and absolute energy efficiency for owners and operators, are those that actively work in concert with the fundamental physical laws of air behavior rather than constantly against them at high energy cost. The Victorian builders 2 centuries ago did not personally have mechanical engineers with sophisticated modern energy modeling software at their desks. They had instead an intuitive and empirically validated working understanding of how ordinary air behaves in enclosed, occupied spaces, and they designed every detail of their buildings accordingly with that physics in mind. The contemporary integration of that proven passive understanding with modern durable materials, modern smart sensing technology, and modern computational predictive modeling offers the genuine prospect of buildings that are simultaneously measurably healthier, measurably more energy efficient, and measurably more physically resilient than anything achievable through purely mechanical approaches alone. A clear future in which old and well-tested environmental physics, far from being obsolete by modern standards, turns out to remain genuinely indispensable for the next generation of healthy, sustainable building stock. Now that you can see exactly how Victorian passive ventilation quietly outperforms most modern sealed buildings in measurable indoor air quality, there is one single small open-able architectural feature that the modern building code in most developed countries has steadily removed from new construction that single-handedly restores most of the lost passive function. In tomorrow's video, we will reveal the exact Victorian architectural element modern building codes have been quietly deleting from new homes for 40 years. The published peer-reviewed evidence that its absence is now the single largest measurable contributor to modern sick building syndrome, and the simple retrofit any homeowner can install in an afternoon to restore its full function at minimal cost. Hit subscribe and turn on the notification bell so you do not miss the small, affordable home retrofit that returns measurable Victorian quality fresh air to any modern airtight apartment or house across a single weekend afternoon.